Hello, so today we are going to wrap up our discussion of intermolecular forces before we move on to surface forces after midterm 1. And I wanted to wrap up by talking about 3 topics. One of them is dielectric constant, the other is steric repulsive forces, and the third is hydrogen bonding and manifestations of hydrogen bonding. So the dielectric constant, which is something we've seen pretty often in the course, it always appears in the denominator in the force and the potential energy functions for all of the different intermolecular pair potentials we've derived. Now the dielectric constant, as it increases, it reduces the Coulomb force. And how does that happen? Well, it turns out that polarizable molecules will associate with dipoles and ions and the plates of parallel plate capacitors in such a way as to lower the electrostatic potential energy of other charges, charged objects, and the charged poles of dipoles. So let's talk a little bit about this and what it and how a dielectric constant arises. And we give it the symbol epsilon. That's really ugly epsilon. Here it is again. And what do we need to have a high dielectric constant? Well, the first rule, as one might expect, is a dipole moment. We want to have a dipole moment. Can we have a dielectric constant without a dipole moment? Yes, but we'll get to that in a moment. But for a basic dielectric material, we generally want to have a dipole moment. How about a second category? So we might have a medium like water, which has a moderate dipole moment, like 1.8 to bi, but it's not the strongest dipole moment, but it has an exceptional dielectric constant, like 80. So how did that arise? Well, it happens that dipole moment alone gives you a dielectric constant because you have orientable dipoles that can orient in such a way to lower the potential energy of charged objects. But if you have lots of them in a given volume, then you can do even more lowering of the electrostatic potential energy. So the density of dipoles matters a lot. And the density of dipoles, so smaller molecule, higher dielectric constant when comparing molecules with the same dipole moment. Now sometimes you have materials or media with an extraordinary dipole moment or extraordinary dielectric constant that can reinforce the polarized state with intermolecular forces. And a good example of an intermolecular force that reinforces the polarized state is the hydrogen bond. And I'm putting the cart before the horse a little bit here because we're going to talk about hydrogen bonding in a few minutes from now, but just take my word for it at the moment that hydrogen bonding helps. Okay, now is it possible to have a dielectric constant from a nonpolar media, like say hexane or benzene or methane? Assuming you could have methane in a condensed phase, which you can. Are those media? Do they have a dipole, or do they have a dielectric constant of 1, like air or vacuum? No, they have a dielectric constant somewhere like 2 to 3. Now, where does that dielectric constant come from if there is no dipole moment? Well, we learned last class about the polarizability of an electron cloud. So it turns out that you can polarize not in a way that allows you to reinforce the polarized state very strongly, but you can align the electrons to some extent to polarize a nonpolar molecule. So we're going to have case 0 here, which is just electronic polarizability. Which is present in all molecules. So it gives us a dielectric constant that is greater than 1 for even nonpolar media. But as soon as you start having dipole moments, this effect becomes minuscule. Okay, let's look at some examples. So how about let's look at methanol, which has a dipole moment of 1.69 dBi. Isopropanol, or isopropyl alcohol, rubbing alcohol, 1.66. And ethanol, which is just the alcohol in beer and wine, of 1.69 dBi. Okay, so these are all really similar dipole moments, but it turns out that they have different values of dielectric constant. So methanol has a dielectric constant of 33, isopropanol has 20, and ethanol has 25. What's going on here? This is purely an effect of the density of the dipole moments. Methanol is the smallest, so it has the greatest dielectric constant. It can fit more of these orientable charges around partial charges of dipoles, or the plates of a parallel plate capacitor, or around charges. So this is an effect of density of dipoles. How about case 2, where we have water, which has 1.85 dBi. We have a molecule called formamide, which has a big dipole moment of 3.7. Then we have dimethyl formamide, which has also a big dipole moment of 3.86. Now, what do we expect here? Well, we know, just because we know that water has a fairly large dielectric constant, and what is it? It's about 78 at room temperature, and even though the dipole moment from dimethyl formamide is bigger by like a factor of 2 bigger, it's also a much bigger molecule, so its density of dipoles is lower, and its dielectric constant is not going to be as strong. It's going to be 37. This guy, however, has a strong ability to hydrogen bond. It's also smaller because whereas this guy has methyl groups, this one only has hydrogen atoms. Now the hydrogen atoms can form hydrogen bonds with the oxygen on nearby molecules, so that reinforces the polarized state and allows this to have a much higher dielectric constant. So this is formamide. It has a dielectric constant of 111. So let's look at a final example, and just to summarize, here we have H bonding and size or density and the dipole moment. Case 3, we have carbon tetrachloride, which has a dipole moment of 0. This is dichloromethane, which has a dielectric constant, or I'm sorry, a dipole moment of 1.6. And chloroform, which has a dipole moment of 1.0. In this case, we have the greatest electronic polarizability here, but that's only case 0. So it it doesn't give us that much in terms of the ability to screen charges or to orient in the presence of a charge. So we have a dielectric constant here, characteristic of a nonpolar medium, which is 2. Now, among these two, we have the greatest electronic polarizability here, but a greater dipole moment here. Differences in dipole moment trump differences in electronic polarizability. So it turns out that the dielectric constant of chloroform is 5 and of dichloromethane is 9. So the lesson to take from this is dipole moment wins over electronic polarizability, which we gave the symbol alpha naught before. Incidentally, how is this connected to our previous conception of dielectric constant that we might have had from, say, second semester physics as an undergraduate, where we were interested in dielectric media in a parallel plate capacitor? Well, if you think about the equation for capacitance, Q over V, or also epsilon naught, epsilon times A over D in a parallel plate capacitor, where this distance is D and these parallel plates have area A. If you charge up one side or the other and you increase the dielectric constant, that allows you to get more charge on the parallel plate at the same voltage. So what does that mean? It means that you're lowering the potential energy of the charges on each side of the parallel plate by increasing the dielectric constant, which is epsilon. So is that consistent with what we've learned on the molecular level? Yes, it is. So even though these are not ions in solution on the sides of the parallel plate, what you have is dipoles that orient so that they lower the electrostatic potential energy so that you can fit more and more charges, a bigger Q, onto the same parallel plate. Okay, that's all I want to say about dielectric constant. We're going to talk a little bit about manifestations of the steric repulsive interaction, which is the interaction that occurs at very small separations. And it is principally due to the Pauli exclusion principle, which says that electrons can't have the same 4 quantum numbers and occupy the same space. So steric repulsive forces, and what am I talking about here? Well, if you look at the Leonard-Jones potential, something like this is W of R. Most of what we've been talking about so far in the course has been over here on the attractive side, where the potential energy decreases as the internuclear separation or center-to-center distance decreases. If the potential energy goes down, we have an attractive force. But as the potential energy goes up, as the particle separation decreases, then we start having a repulsive force that's due to this steric repulsive effect. So this is what we care about now. And this is quantum mechanical in origin. So this is the Pauli exclusion principle, and it says that the potential rises steeply at small separations. Okay, now there are a few different ways to measure the sizes of atoms. So the steric repulsion is intimately related to the fact that atoms take up physical space. So what are the sizes of atoms? Well, the size of atoms given by like a radius, r, not the internuclear separation, but the radius of an atom, can change depending, it doesn't really change, but we use a different radius depending on what we are talking about or trying to calculate. So let's look at some ways from smallest to largest of ways that we can estimate the sizes of atoms. So first we have the Bohr radius. The Bohr radius is the radius at the maximum radial probability. That is the maximum of the square of the wave function. So for the hydrogen atom, you can calculate this, and it is R equals 0.053 nanometers for the hydrogen atom. Some of you might have done this in a chemistry class or a modern physics class. Okay, now this actually represents kind of a small radius because the wave functions, they start to overlap. Even though the maxima might be quite far apart, the wave functions still overlap. So as soon as the wave functions start overlapping, you have these unfavorable exchange interactions that are characteristic of the Pauli exclusion principle, and you therefore have a repulsive force. So next up, you have the radius that arises from a calculation of the B parameter in the van der Waals equation of state. So radius from the parameter B in the van der Waals of state. And this is from class 2, I believe, episode 2. We have R equals 3B over 3 pi times Avogadro's number to the 1/3 divided by 2. Now this value is smaller than the equilibrium value, which is the van der Waals radius, which we're going to talk about next. Why is it smaller? Because the particles, as they're swimming around, as they collide, they can get a little bit closer than equilibrium before they bounce away and scatter off the walls and other particles, and then they bounce, and they can actually get a little bit closer than is comfortable. So they can get a little bit closer, and maybe the distance that they get, they might be to toward the unfavorable part of the Leonard-Jones potential, where it starts becoming repulsive. But if you average them all out, sometimes they do tend to get closer than too close for comfort. What is comfort? Comfort is the van der Waals radius. The van der Waals radius, the van der Waals packing radius as in a solid. So this is our van der Waals, which is almost always what we're talking about in class. This is almost always what we mean in class. Now what is this? This is the trough in the Leonard-Jones potential. Here is the trough. And that is where the attractive and repulsive interactions give you a minimum in potential energy. You can also have a radius which is slightly larger from calculations from liquid density. Which are going to be 5 to 10% larger than our van der Waals, except H2O, in which it's actually going to be a little bit smaller. The distance is actually going to be a little bit smaller in the liquid compared to solid ice, because in solid ice, which we'll talk about in a few minutes, has these directional bonds and these tetrahedral arrangements where the density actually increases. So this is well known. Like if you cap a beer and you put it in the freezer, the beer bottle might explode. Okay, so these are from smallest to largest. But there is also something that's not on the scale, and that is the covalent radius. And the covalent radius says that if you have some atom, let me make sure that you can see, yep. Okay, so you have some atom that has R van der Waals, and then you bond them together, the chemical bond actually brings the nuclei quite close together. So R van der Waals is greater than R covalent, where R covalent, the rule of thumb is that it's R van der Waals minus 0.08 nanometers. And for the H atom, the hydrogen atom, R van der Waals equals 0.12 nanometers. So something to notice here is that R van der Waals 0.12 nanometers is much larger than the Bohr radius. And the covalent radius is 0.035 nanometers. So here's hydrogen and here's hydrogen, and when they make a bond, they get really close together, and then they become this H2 molecule, where the new covalent radius is much, much smaller than the radius was of either atom separately. Okay, so what happens when we have molecules in a liquid or solid state, and what are some manifestations of these steric repulsive effects? Okay, there are effects on packing. So how about branching? So look at these two molecules. Remember, in organic chemistry, each line is a bond. Each vertex or endpoint is a carbon atom. If a carbon atom is not already connected to 4 carbon atoms, then you assume that it is connected to enough hydrogen atoms to add up to 4 other things to which it's bonded. So CH3, CH2, CH, CH2, CH2, CH3, CH3. Another way of writing this would be CH3, CH2, CH, and then in parentheses for the branch, we write CH3, CH2, CH2, CH3. Now what happens here? Which one has the lower melting temperature? The one on the left. Why? Because this can't pack as efficiently as the straight chain alkane does. This little branching point is going to create a kind of a point that prevents close packing. So it's going to be easier to supply enough thermal energy to the system to allow it to become a liquid. Lower Tm, but how about the boiling temperature? Turns out that they're similar. Once you have these two things in a liquid state, since this is already just moving around like a liquid, it turns out that all bets are off and that both have a similar Tb. Okay, so this is an effect of branching. How about an effect of double bonds? So let's look at Stearic acid. This is the 18 carbon fatty acid. This one is the completely saturated C18 fatty acid, and it has a melting temperature of 70 and a boiling temperature in degrees Celsius of 383. Now let's look at oleic acid, which is an unsaturated version of the C18 carboxylic acid. This is oleic acid. It comes from olive oil. This is a cis double bond. And it has a melting temperature. You might guess, based on the previous example, that it's lower, and in fact it is. The melting temperature is only 13 C. Oleic acid, olive oil, we know olive oil is, of course olive oil is not all of this, but it has a lot of it in it. And it's a liquid at room temperature. But its boiling point, again, once it's a liquid, it's sloshing around, there's no regular order, packing isn't that important. So the boiling temperature is similar, 360. What if we just look at one other example, and this is Oleic acid. And instead of a cis double bond, it has a trans double bond. And the trans double bond is what you might get in a trans fat, for example, where we have incompletely converted this one into this one, and instead of converting this to a saturated bond, we've just succeeded in isomerizing it to the trans bond, and this is how you increase your low density lipoproteins and all this bad stuff by having trans fat in your diet. But anyway, this class is not about that, but this still packs better than this, but not as good as this. So its Tm is 43, and the boiling temperature is 288, but at 1/8 of atmospheric pressure, and I couldn't find the value for 1 atmosphere, but you can expect that it would be similar at 1 atmosphere. Okay, so anyway, you can kind of see the trends here. You can take a look at a bond and get some idea to how it's going to pack in the solid state. Let's think about packing arrangements. Not every packing arrangement is equal. You can have amorphous systems or crystalline systems that are going to affect the thermal transitions, going to affect the boiling and melting temperatures. So we have 3 packing arrangements that we're going to discuss. The close packed system. Now this is just for hard spheres like billiard balls. We have 74% of the volume occupied and 12 nearest neighbors. Second is random close packing, which is the tightest arrangement you could possibly get without having a regular repeating structure. And this gives you 64% volume filled. This has 8 contact points on average. Now there's a range of amorphous structures like this that you can have. You can have close packing amorphous structures, but you can loosen up the packing structure before flow begins. Imagine like a gumball machine or a ball pit. You can have random loose packing, which has only 55% of the volume occupied by the spheres, and this is the threshold for flow. So if you go down to 54% volume fraction of hard spheres, then those spheres are going to be able to flop around, whereas these would be held in place as you say inverted a box of balls that had this packing arrangement. Okay, I need the whole board for this argument, so I'm gonna erase this. Let's think about the liquid structure. So transitioning from a face-centered cubic structure, as we increase the temperature, we liquefy it. How does that change the distribution of other molecules in the mix? Okay, so starting with this arrangement, This is a face-centered cubic structure where we have atoms at the vertices and atoms at the faces. And we have these are the centers. So really we're talking about atoms that are spherical, but these are the centers of the spheres. And we have 12 nearest neighbors at a separation of r equals sigma, the hard sphere diameter. We have 6 at r equals square root of 2 sigma, and we have 24 at r equals square root of 3 sigma. Just a little aside, a couple of years ago when I taught this lecture, I wrote FCC at 0K on the board, and one of the students raised their hand and said, "What's ATOC?" And I responded, "At 0K, or a Klingon name." And everyone laughed, and that was funny or whatever. And then a few minutes later, somebody raised his hand and said, "What's ATOC?" And then everybody laughed again. And I said, the students are right to laugh at you. Just kidding. Okay. Everything about the story is true, except I didn't say that they were right to laugh at. Anyway, okay, so what happens to this distribution as we start to raise the temperature? So picture a solid at temperature less than the melting temperature. And this is the number of neighbors, n, and we have r, and our demarcations here are going to be integer numbers of the hard sphere diameter. So at 0K, we have these little delta functions. So 12, 6 at square root of 2, then 24 at square root of 3, and then integer numbers, we have 12, and so on. So this is at (0K). But then as we increase the temperature to the temperature less than Tm, we get broadening of the distribution just as molecules start to, oops, I did not mean this to be some kind of reentrant surface. Like this. So the profile broadens at T less than Tm just because the molecules start to vibrate about their equilibrium positions. Okay, how about in a liquid? Is a liquid completely unstructured from the standpoint of its nearest neighbors? No, it's not completely unstructured. Statistically, you're more likely to find molecules that are 1 sigma away from you, 2 sigmas, and 3 sigmas away from you, and so on. So in a liquid, T greater than Tm, you lose this crystal structure completely, but it's not completely random either. So the distribution, which we will plot in terms of the density of molecules away from some central molecule over the bulk density and we expect some oscillating function about 1 sigma, 2 sigma, 3 sigma, and we can't have any density at smaller than the hard sphere diameter, but we end up with some oscillating function that slowly decays. And what this means is as you get farther and farther away from some central atom, you'll accumulate enough disorder by virtue of the fact that you're in a liquid and there's all this randomness, that if you're, say, 10 hard sphere diameters away from the central molecule, you effectively have the bulk density. Whereas the nearest neighbors tend to be concentrated at multiples of the hard sphere diameter. Okay? All right, that's all I wanted to say about this topic. I want to say a few things about water, hydrogen bonding, and the hydrophobic effect, and then we will be done. Okay, let's, what do we know about water? Water, H bonding, and hydrophobicity. So for water, some facts about water. The density of the solid is less than the density of the liquid. The dielectric constant of the solid is greater than the dielectric constant of the liquid, which is a bit unusual because in a liquid, you're able to reorient the dipoles, where in a solid, you generally are not able to. So water has some other type of polarization mechanism, which is not fully understood, but it's a very interesting frontier of investigation. And you have a higher proton mobility for ice. So it's actually possible to have protons or naked hydrogen atoms propagate through liquid or through solid water. So what does water look like in terms of its hydrogen bonded arrangement in the solid state? Take me a minute to draw this. So draw oxygen atoms at the vertices of a tetrahedron. And the hydrogen bonds are these dotted lines. If you can speed up the YouTube video, now is a good time to do it. And the vertices of a tetrahedron are something like this. Did not give myself enough room in this drawing. Bear with me. Okay, this is the tetrahedral structure of liquid water. It has 4 nearest neighbors. Although there are an average of 5 in the liquid. But only an average of 3.5 hydrogen bonds per molecule in the liquid. What are these bond lengths? Well, the actual covalent bonds between oxygen and hydrogen are about 0.1 nanometers, whereas the hydrogen bonds have lengths of 0.18 nanometers. And just for significant figures, reasons of having accurate significant figures, 0.10, 0.18. It was previously expected that the hydrogen atom would just switch back and forth, but it doesn't really do that. It really does persist on its parent atom more than it does switch over to the other one. So what we see from this is that this bond length is actually a bit longer than one would predict just based on summing the van der Waals diameters of water, which would give you 0.226 nanometers. But this gives you 0.28. So in fact, there's this ability to align the hydrogen bonds toward each other actually allows the nuclear separation to be a little bit greater than you would expect. 4 nearest neighbors, this is a dot, 4 nearest neighbors, as opposed to what? In a close packed system, you would have 12 nearest neighbors. So water has fewer nearest neighbors. What about the hydrogen bond? The hydrogen bond has X bonded to H, hydrogen bonded to Y. This is an H bond donor. And this is an H bond acceptor. And this hydrogen atom is not actually shared. It's actually closer to the parent atom. And it gives you 10 to 40 kilojoules per mole, or 5 to 10 kT per bond at room temperature. All right, you can pause it here for a moment before I erase it. So hydrophobicity. We have kind of an intuition that oil and water don't like to mix, but we learned early on in class that actually a single oil molecule in a vacuum and a single water molecule in a vacuum actually do come together by the van der Waals force, the three components of the van der Waals forces. Now, why do oil and water seem to repel in a vacuum or in a liquid environment? And why do oil molecules coalesce when they're in an environment of water? So why does salad dressing break apart? So hydrophobicity is driven by a loss of H bonds with a solute. So if the solute can't hydrogen bond with the water, then the water says, I want to keep my hydrogen bonds with the other water molecules in the beaker. So what it does is reorganizes, H2O reorganizes to form a cage or a clathrate type structure around the solute. Now dissolution is in general encouraged by greater entropy in the solubilized state, but it is often discouraged by an unfavorable enthalpy of mixing, an unfavorable mixing of two different types of molecules, because usually the one with the stronger interaction wants to, the medium with the stronger intermolecular forces, medium with the stronger van der Waals coefficient, wants to maintain contact with itself and not allow other things to come in, solutes to come in, even though entropically it would be favorable for them to mix. So there's always this push and pull in solubility rules. But this cage structure is entropically unfavorable. So there's an entropic favorability of mixing when you have something that's as strongly hydrogen bonded as water is. So it's entropically unfavorable. So imagine transferring butane to water. We have delta G of transfer equals delta H minus T delta S, and our delta H term is minus 4.3 kilojoules per mole, plus our T delta S term is 28.7 kilojoules per mole, because we lost entropy upon mixing, to give us a net total of 24.5 kilojoules per mole. And the delta G of transfer is proportional to the surface area of the molecules and the surface energy of a hydrocarbon. So these are interfacial free energies. Gamma I for a water hydrocarbon is 40 to 50 millijoules per square meter. And for air, hydrocarbon, we have 15 to 30 millijoules per square meter. Give you a second to write this down. I just have one more board and then we're done. So we can actually use this idea of an entropically unfavorable clathrate structure to predict an attractive interaction between two, say, methane molecules in water and compare it to the interaction in vacuum. So the hydrophobic interaction, the methane interaction, the methane van der Waals energy is minus 2.5 times 10 to the minus 21 joules in vacuum, but it's minus 14 times 10 to the minus 21 joules in water. So we have a huge increase. Still, this is no complete theory that it completely predicts all of the hydrophobic effect. Experimentally, what we find is that the van der Waals energy of the hydrophobic interaction falls below kT at about 2 nanometers and greater separation. So it's actually quite strong at nanoscopic distances between the van der Waals diameter or the van der Waals radius and 2 nanometers, whereas that's a 7 times greater range than the van der Waals interaction in a vacuum, where it falls over by 1 over r to the 6. So experimentally, what we find is that W of r is less than kT at r greater than 2 nanometers, and this is a 7 times greater range for this condition than W of r equals minus C van der Waals over r to the 6th for hydrocarbon in vacuum. Okay, so still no complete theory on the hydrophobic effect, but it's really responsible for much of biochemistry and drug design, and anytime you're dealing with anything in a water medium, it's important to know what's going on and to be able to use intermolecular forces to be able to predict what's going to happen. All right, see you next time. Thanks.